Okay, so in this video, we want to discover some interesting properties of logarithms, things that you're allowed to do with logarithms that may not be obvious, and it will help you simplify calculations in the future. And we also need to make sure that we stay away from some of the things that look like they might work, but are really imposters. So let's start off by looking at these two expressions here. We have log of some base a of a product p times q, and log base a of a quotient p divided by q. The question here is, are these equal to something else that might be easier to use in the future or more useful or help us do problems in a better way? So the big question for today, I guess, is what's legal with logs? There are two key facts I'm going to use throughout this video. I'm going to write them up here, and if they don't look familiar, if you don't like what you see, you need to go back to the previous video and look back at them because they were explained in more detail there. But the first one is going to be, so let me write this here, key facts that we're going to use again and again to help us here. Number one is that a to the log base a of stuff, okay, and stuff is obviously some expression, I'm just using that as a general catch-all here, is equal to stuff. That's a composition property of inverse functions. So if you don't like that, go back and review the last video to familiarize yourself with that a little bit more. And then the other one is log base a of a to the stuff is also equal to stuff. Same reason, that's the composition property of inverse functions. So you're going to see those two things pop up again and again in this video as we try to make sense of these expressions and what they're equivalent to. Okay, so let's look at log base a of p times q. And what I'm going to do is I'm going to use property or equation number one here to rewrite p and to rewrite q. So log base a of p times q can be rewritten by transforming p and q into something else. So by this equation, p is going to act like the stuff. So p is the same as a to the log base a of p. So that's what I'm going to write here instead of p. A to the log base a of p. And then I'm going to do the same thing for q. Q would become a to the log base a of q. So again, that may not look very friendly or something you would do on your own as being obvious, but it's true using the first key fact. Now, inside the logarithm here, I have two things that are being multiplied that have the same base. We already know that there's a rule for that back from chapter 1, and the rule says you're allowed to add the exponents. So I now have log base a of a to the log base a of p plus log base a of q. And now I'm going to go ahead and use property number 2 up here, key fact number 2, which says if you have log base a of a to the stuff, which I do, log base a of a to the stuff, then the answer is equal to stuff. So this can be rewritten as just what you have in the exponent there, which is log base a of p plus log base a of q. And so what we end up with is we started with this expression up here, and we ended with this expression down here. And so we now have a rule or a law or a legal move, however you want to think about it. But it says this. It says log base a of p times q, two things being multiplied, is the same thing, believe it or not, as log base a of p plus log base a of q. Okay, not obvious. You wouldn't just guess that that was the case. You'd probably think it had something to do with multiplying the two logs. But here's what you have. Here's a little calculation that verifies it for us. Maybe it's more believable if you see what a calculator says. Okay, so I used a calculator to evaluate log base 2 of 6, and I got 2.5849, etc. 6 is the same as 3 times 2, so our rule says that that could be the same thing as log base 2 of 3, right here, plus log base 2 of 2. And when I add those two things together, I get the exact same answer, 2.58496. All right, so it's a rule that we may use in the future if it helps us, and from time to time it will help us. Now, you're probably going to guess that there's a similar rule for division, and there is. So let's just quickly go through it. It's going to have many of the same steps. Log base A of P over Q can be rewritten, first of all, using the first key fact there in red. So P is rewritten as A to the log base A of P, and Q is rewritten as A to the log base A of Q. We have a rule that says when I divide expressions with the same base, I may subtract their exponents. Keep the base the same. So this becomes log, sorry, I forgot to put the A here, log base A of A to the log base A of P minus log base A of Q. And now you use property or key fact number 2 that says log base A of A to the stuff is just the stuff. So you get log base A of P minus log base A of Q with everything else canceling out. And so the rule for division says that log base A of P over Q is equal to log base A of P, and not plus this time, but minus, which I think makes sense because now we're talking about division. Here's a quick snapshot from the calculator. Again, we're going to use log base 2 of 6, which is that 2.58496. I could think of 6 as 12 divided by 2. So you can see the expression for log base 2 of 12 minus log base 2 of 2. And lo and behold, we get the same numerical answer. Okay, now let's look at this expression here. Log base A of P to the Q. So now I have a expression on the inside of the log raised to a power. And again, I'm going to use that key fact that we had in the last slide and rewrite this as log base A of A to the log base A of P. That's what P is equal to. And that's being raised to the Q power. And I should probably put this in brackets here so we understand where the Q really is. It's all on the inside of the log. Okay, now we have a rule from chapter 1 that says power to a power allows us to multiply the exponents together. So on the inside, I could have A to the, I'm going to put the Q in front here, Q times log base A of P by multiplying these two exponents, Q and log base A of P, up here in the top. Okay, and then we're going to use key fact number 2. It says log base A of A to the stuff, which is what I have here on this line, is equal to the stuff. And the stuff is Q times log base A of P, which means we have a new rule that says if I have the log of something to a power, P to the Q, for example, that's allowed to be rewritten as Q times the log base A of P. So in other words, the exponent of the argument is allowed to come in front of the logarithm. Again, not an obvious property that you would just guess is true, but there it is. Here's a little evidence from the calculator that may convince you. Log base 2 of 9 is 3.169925, and 9 we know is 3 to the second power. So 3 to the second power, I brought the 2 down in front, and I have 2 times log base 2 of 3, and I got 3.169925, the same number. Okay, so we've seen 3 laws verified algebraically and then showing you some evidence on the calculator that they're true. All right, what about rules for when you have the log of a sum or the log of a difference? Are there rules for that? And if so, what are they? So it would be very tempting to do what looks like distribution and make this log P plus log Q, okay, because that's what we normally do when we see something in front of a parenthesis that has a sum or a difference, right? That would be probably the first thing you would guess and want to believe is true. It's convenient because it goes with what you're used to seeing. Here's what happens when I go to the calculator to see if that's true or not, okay? I have log base 2 of 9 is 3.169925, and 9 is 4 plus 5. So the question is, could I have made log 4 plus 5 into log 4 plus log 5? And we can see clearly that no, that is not the case. So this rule, though it looks tempting, is one of the imposter rules for logs. Same with this one over here. In fact, there is no rule for log of a sum and log of a difference. It's unfortunate, but we have to learn to recognize that there is no rule and not misapply an imposter rule. Okay, let's look at one more rule here. This one used to be a bigger deal before big-time graphing calculators could do logs for different bases. Okay, but here's the assumption here. You have log base A of P. You want to evaluate that number, but let's say you don't want to be in base A. It used to be that your calculators only had two log buttons, the natural log button and the base 10 log button. Okay, so being in any other base was kind of a problem. So this is a way to get out of base A and get into any base you want. Okay, and I'll explain how that works here. So, first thing I'm going to do is I'm going to say, okay, log base A of P is equal to some number. You could call it Y, X, K, anything. I'm just going to call it question mark for the moment. And let's rewrite this, okay? Rewrite this in exponential notation. What does it mean in terms of exponents? And that's going to be a convenient tactic you use a lot in this unit when things look a little bizarre, is maybe I could rewrite it and make more sense of it a different way, okay? So exponential notation means this is my base A. The answer here is the exponent, so A to the question mark equals P. You're going to take the log of both sides of this equation, and you can use any log you want. Since the calculators, and you're probably most familiar with either log base 10 or natural log, those are going to be the natural choices. Okay, and this is operation that we're going to get into more in the next couple sections, is taking the log of both sides of an equation. It's an operation. Not multiplication, you're taking the log of both sides. So how you write it is log any base you want, so I'll just use base 10, okay, just for fun. Log of A to the question mark equals log of P. Over here you have an expression to a power, and we just saw a couple slides ago that you're allowed to bring the power down in front of the log. So now you'd have question mark times log of A equals log of P. And so now you can solve for question mark. And you'll notice now that question mark is equal to two logs that have the base that you chose, in this case base 10. If we go back to the beginning, what was question mark equal to? Question mark was equal to log base A of P. Okay, this is called the change of base formula, because you've changed the base from log base A to any base you want. We drew up base 10 here. It doesn't have to be base 10, it could be base anything. Back up a couple steps. So this is the change of base formula. Used to be a bigger deal, but your Inspire CAS can handle logarithms of any base if you had to use a calculator to approximate something. Okay, and just here's a little verification on the calculator. Okay, log base 2 of 5, for example, used to be a problem in the calculator. So you could have converted that to log base 10 of 5 divided by log base 10 of 2. And you notice you get the same numerical value for both. All right, the way I used to think about this is if I had a log I didn't like, all right, I could make it log of anything I want of the big number, okay, divided by log of whatever I want of the little number. So I kind of thought of the P and the A here as almost like a fraction, and that's what happened on the right side there.